So the first part of the poster is background and motivation. Here we basically say that DAS has been used to document seismic strain rate, traditionally from S waves. This is because DAS typically measures the phase shift caused by axial strain, or in other words, infinitesimal or like very small extension or shrinkage of the cable along its main axis. So S waves with components in the azimuth of the fibers are easily documented, so to speak. But at the same time, P waves have also been documented in DAS recordings, although except for the case of a very shallow local earthquakes, they do not necessarily have a, so to speak, longitudinal component in the cable. After all, they are compressional waves. People have generally attributed the appearance of P waves in DAS data to oblique arrivals in DAS. You can think of this as pushing a piece of paper on your desk at an angle. It is true that you're indeed pushing it towards the desk, but at the same time, it'll also move horizontally. So there's like a horizontal component. And this is why people think there are P wave appearances in the DAS data. But in Yolin's paper, where we detect earthquakes in the Sanriku dataset, it seems that earthquakes of all sorts, at all sorts of angles, have very good P waves, regardless of where they are. Figure 1A, for instance, shows the location of Yolin's detections, and they're a pretty good part of JMA dataset, as we show in Figure 2B. This is because the general trend of mechanism in the area of a study, as we compute from all the events ever in the CMT catalog, shows very strong S-wave radiation coefficient. So in other words, we would expect a more or less quote-unquote complete data set from the duration of the deployment. So in the second part, in the middle column, we basically show two general mechanisms for DAS P-wave recordings. Mechanism 1, which are the smaller beach balls to the right of the figure 2, is the oblique component, as I described before. Mechanism 2 is the big beach ball to the left, and you can see it like a vertical incidence with absolutely no horizontal component. So going back to Sanriku, we are showing in figure 3 the computed incidence angles at the cable's midpoint for earthquakes all around the region in 4 depth range. This is just to save some computation time to discretize depth. Each point of the region in these figures are colored based on their I0 or incidence angles. We're showing our detected earthquakes as circles, and here we're also picking 3 of them and showing them with stars of different colors at different depths. So on the right, to figure 3 and figure 4, we show records from these stars. And the important thing is that the red and orange records from the red and orange stars show P waves. It's interesting because these earthquakes or stars are right under the cable with I0s technically equal to 0. So the P-wave records from non-oblique arrivals are not a fantasy, and they're very much real. We propose a mechanism for them, which is basically the bottom part of the middle column. And it's the response of a cable to a normal force, which we show with Fx. We set up the dynamics and show that the steady state, where we ignore time, has a solution in the form of a wave equation, and its spatial frequency depends on the cable properties and the incoming wave frequency. We can derive a similar equation for the case where we ignore space and just solve for time, and the equations are going to be similar. So in other words, the P waves that we observe in this are sort of emergent. They're expected to have a sort of a damped appearance, and they're going to be fluctuations in the cable. It's not like the axial strain. The actual cable is going up and down like a rope, and you have maxima and minima and so on and so forth. And this is kind of different from the oblique arrival mechanism, where you sort of consider the cable to be fixed. So finally, column 3 is our preliminary results. Here we're showing examples of deep events with different incidence angles. The record on top is from the magnitude 6.3 C of Okhotsk earthquake, which has a more or less oblique arrival with very crisp, sharp P waves. And the frequency is localized in the spectrogram around 1 to 3 hertz, which is what you expect from the earthquakes of this size. And sort of mechanism. But the one at the bottom has a smaller I naught, and as I mentioned before, has a more diffuse character with a, so to speak, banded or modal frequencies, as you would expect from an oscillator, which has selected frequencies, as we can see in the spectrograms. So this agrees with our model, and the next step for us is to compute the frequencies, which I have basically winged here. The result would depend on the cable structure, etc.